Alright, let's make a start. Thank you. So today we're looking at tangents, so we're going to look at both the graphs and some equations. So just remind you about the tangent. So if we draw a line down here, and then we've got an angle, when we extend out to this line, this tangent, when we extend out, the length of that is the tan of that angle. So here's an animation here, so I'm going to change this, and we'll change the angle, and it's going to plot over here. This line just will move, and this point will go up here, up the tangent, and it will plot the length of the tangent. So at the moment, the length of the tangent is 0, so on the graph at 0 degrees we're down here. But then as we increase the angle, and this is in radians, so as we increase that angle, the length of this tangent, and then it's plotting the point corresponds to the length of the tangent. Oh, sorry, the 0.68 is the length of the tangent. 0.6 here is the angle in this angle in radians. And so we go up here. As you can see, it's getting longer and longer. So it's getting longer and longer. The graph is curving around. And then when we get to give me this next angle 1.6 is over here. So what we need to do is we need to trace back then. The tangent, remember, is over there. So we're going to trace back because down here is negative. So you have this there, and then bang, it all jumps around here. So your poem 2 here is asymptote. And it keep going around, it comes there, back, and then we go around into, and again here, the angle we're talking about is this one around to here, but we trace back. And that's the length of that tangent, so back into positive, and so on. So you get something that looks like that, which, if we plot that, looks like that. So you can see for tan, the period is pi, thank you very much. And the asymptotes, of course, if the period's pi, they're pi apart. And then if we're just using our origin as our start point, our first asymptote would be half pi each way, and then pi after that. Other significant point is this one here that you can use. So this angle here would be pi on 4, thank you very much, and 1. So tan of pi on 4 is 1.
Is that pi on 5?
Pi on 6, pi on 3.
Then how's that pi on 4?
Pi on 2, halfway, pi on 4.
Okay.
These are what, 1, 2, 3, 4, 5, 6, so they're pi on 12s. Each of those. Alright, now should be hopefully no surprise to you. Transformations. Number in front here stretches it this way, so instead of being now up at 2, this number in front is going to do what? Make it smaller if I make it bigger, or make it bigger if I make it smaller. Alright, so it's the same. And that relates to the period. Thank you. No.
Oh. That's where you're wrong.
pi over n
Pi over n.
for tan. Pi over n, the period for tan is pi. I'm going to write all this down. All right, the number in here is going to move it left or right. Yeah, 1.57 is about pi on 2. And this one here is going to move it up or down. All right. So let's write all of that down. All right, so I'm going to go look at the standard y equals tan x first up. So our standard y equals tan x has a period of pi. We have vertical asymptotes.
So I'm like every Friday.
He just needs to get yelled at.
Yeah, I agree.
He just needs to get yelled at.
I feel like you have that trip because you wish that was you.
No, I don't. I'm just saying because he like doesn't care.
Alright, so the first vertical asymptotes at x equals pi on 2 and then every pi both ways. Intersects the x-axis. At x equals 0, and again then every pi. And our key point
Yeah, I know.
is pi on 4 and 1. So if we're going to draw that,
What's a key point?
For this.
It's just a point that you can
Like
draw
it's-
in.
It's like one that's
Oh,
always
yeah,
the
so-
same.
A
Like,
point that you can easily find.
point you can easily find, exactly. And because the tan of pi on 4 is, what is it, 1? The tan of pi on 4 is 1, that's the point we're going to easily find. So we know if there's a dilation, it's going to either move, that point's going to move depending on whether it's, so this A here, for example, can move it up there or down. So yeah, it's just something we can easily find. All right. So if we are looking at that, so we've got asymptotes at 1 pi on 2 and then every pi after that. And it goes for both ways. Alright, so it goes both ways. It intersects the origin, the x-axis there, and then because the period's pi, then it does that at every pi as well. Again, both ways. And pi on 4, which is halfway, and 1 goes through there. And then curves around like so. And then depending on what domain we're after, we just continue the pattern. Alright, so let's put the transformations in. All right. So, the thing you need to remember about the period with the transformations, sine and cos, it's 2 pi on n because their periods are 2 pi. But for tan, because its period is pi, the period is pi on n when it gets transformed. Alright, so the number that's here, the pi up here is related to the period of tan. So that's why it's pi. We've got, of course, a dilation from x-axis of A, and then we have translations, and they're the H and the K as well. And K in the Y direction. Now our first asymptote it was pi on 2, but when we have put the dilation in, it becomes pi over 2n. Alright, so let's have a look at an example. Now I've left something off this, just realised. If there's a translation, so the H should be in there as well.
Plus H or minus H? Plus or minus H?
Plus H. Plus H.
If you want, you could just use the thing.
If you can. Alright, so period on this one is pi over n, and n is
2. Yeah.
so pi on 2. We have a translation.
1.
Up 1.
Yeah.
First asymptote.
Pi over 4 plus 1? No. Pi over 4.
It's pi over 4.
So if there's nothing there, you don't.
Because we haven't.
It needs to be, there's no H there.
Yeah, so we haven't translated left or right. Pi over 4. And I left a bit off the end which says for x between negative pi and pi. All right. So we get translation 1 up. So that's the way I like to do it. I like to just put a little dotted line here so our mid line has been moved up. So the point that we will start at, instead of being through the origin, that gets moved up 1 as well. It's going to work through there. Our first asymptote is at pi on 4. I'm going to do them in green. And then, because the period's pi on 2, every half pi, asymptotes. And then this point here, again, every half pi is where it goes through our midline. Just following the patterns. Now, this next one, we're around that key point, which was pi on 4 and 1. Because we've got this dilation of 3, it would be halfway here. Instead of just 1 above, it will be 3 above. So up here at 4. So it's been stretched quite a lot. And just follow the... Oops, that looks a bit straight, that bit, doesn't it? Just follow the pattern. Yes? Anything with that I went through too quick? Left anyone behind? They're not as nice as sine and cos graphs. Just got an ugly shape.
So if you include the translation, is the key point pi on 4n plus k?
Yeah, it sounds right. And then, and then there's the h for in the y direction. But really, just another way of looking at it is look at the pattern. That key point is halfway between there and your asymptote, and usually it's 1 above. So it's halfway and then 1 above, or halfway and 1 below, and then whatever your dilation is, just stretches it up that bit. Whatever way of thinking about it's easier. That's the way I do it. I just go that the key point's halfway between there, and it's 1 higher. Dilation of 3, so instead of being 1 higher, it's 3 higher. I want to try and use the patterns as much as possible. Because really, once you've got this bit here in, this first bit, the rest all just repeats. Over here, it's just flip it around 180 degrees and it goes down there, and then that just repeats as much as you like. Alright, so the other bit of this is equations. So I'll do an example of an equation. Do you want 2 examples? Alright, so equations with tangents, so these are just like ones we were doing with sine and cos. So same techniques. Alright, so tan half x minus pi on 4 is equal to minus 1. So, when's tan negative?
Second and fourth.
Second and fourth. So the angles we're looking for are going to be in the second and the fourth quadrants. So we now need to know what this angle is in here. Will be the same as that. Our reference angle, and our reference angle is related to tan minus 1 of 1. So remember, the minus we've used to figure out which quadrants, and then we use the 1 to figure out the size of that angle. And that would be pi on 4. Right, now we have a bit of an issue, and the bit of an issue is our domain is written in terms of x, and the angle that we're taking the tan of is all this stuff. So we need to get the two somehow consistent with each other. Now the easiest way to do that is to change this one here to be the same as that. So if we have x being an element of somewhere between negative 2 pi and 2 pi, then x minus pi on 4, we would take pi on 4 from that, which is minus 8 minus 9 and 8, 7. Alright, then we've got this half out the front, so we just multiply everything then by half. All right. So what that means is that we can come backwards. All right, we can come backwards, but the furthest we're allowed to go backwards is 1 1/8. So 1 1/8 would be here somewhere. So we're not going to get to that one. So we can carry around to there. So what does that mean? That means that this half x minus pi on 4 would be equal to negative, because we're going in the negative direction, and our reference angle is pi on 4. And we're allowed to go in the positive direction to 7 pi on 8, so 7/8 of pi, so I can go around there. But I'm only allowed to go a little bit less than, so I can only get around here. Now around here, that angle in there is short of pi, so that angle in there is pi minus pi on 4, which is how much of pi? 3 pi on 4. Alright, but in the original question, getting back to our domain is, it talks about x, so we just need to rearrange that to get x by itself. So to move this half, what are we going to do to both sides? Times by 2, yep. So when you times these by 2, their denominator will become by 2, so it goes into 4 twice. Then to move the in pi on 4, we've got to add it. Might have been easier to leave that, but anyway, not to worry. So minus pi on 2 plus pi on 4 is how much? Minus pi on 4. And the other one, 3, 6 plus 7 pi on 4. Alright, any questions about that process? Yes, Ethan.
How did you get the reference angle?
Right, so the reference angle relates to the 1. So the tan of something, some angle, being 1. So inverse tan of 1 is pi on 4. So this angle here and there, back to the x-axis is then pi on 4. Because the tan of pi on 4 would be the 1 part.
Ah,
Alright, because we noted we wanted to be minus 1. We used the minus part of it to say
yeah.
which quadrants we're looking at. And then we used the number part of it to figure out our reference angle.
Yeah, so that's...
And because it's tan, we're tan minus 1 of the number part.
that
And in this
is-
case it's pi on 4.
Yeah. Alright, nice.
And so that then means that this angle here is pi on 4. And so that doesn't matter whether it's sine, cos or tan. You can use that strategy. Anything else? Alright, I'll do one more. Example. Just make Alright, so this one we've got asked that sine 2x is equal to cos 2x, and we want to find all x's where that's the case. So we've got a sine on one side, a cos on the other side, and so somehow we need to bring it all together. And we know that sine and cos, when we put them together in a particular way, they are tan. So if I can put them together in the particular way that tan is sine over cos, that might make life a bit easier. So to do that, I need to rearrange by dividing cos 2x both sides. So the right hand side is now going to be equal to 1. So we've now got tan 2x equals 1. All right, so tan positive, which quadrants? First and third. And the number part is 1, so our reference angle tan minus 1 of 1 would be pi on 4 again. All right, now we've got the same thing, we've got x here, but our angle part is 2x, so we need to change that domain to fit with 2x. So if the domain of x is between 0 and pi, we change the domain to 2x because that's what we have here, which would then be 0 to 2 pi. All right, our sketch. So we're in the first and the third. Our reference angle's this one here, which we know is pi on 4. So 2x. All right, we're allowed to go from 0 to 2 pi, so we get to there. That's how big? Pi on 4. I can keep going, so I could get round to the next line okay. And that angle all the way around there is pi plus pi on 4, yep. Up is 5 pi's on 4. The original question asked us to solve for x, so we need to divide by 2, yep, and when we divide it by 2, those denominators will become
2, 8.
8.
Yeah.
Right, so when we divide by 2, the 2 ends up down here, doesn't it? So it then multiplies by that. Yes, question?
What's that in front of the X on the second line?
Oh yeah, that's a really bad 2.
Nice.
Even for me, that's bad. All right. Now, in relation to these, if I drew the graph of sine 2x and the cos 2x, and in relation to this, what will these points on those graphs be, do we think? Intercepts. So if I drew sine 2x, I would get something like this. And when I draw cos 2x, I get something like this.
Yeah, that's
All right. And so these points we've found, those x values
also the intercepts of each other.
are where the intercepts are. So at x equals pi on 8 and 5 pi on 8, these two graphs, that's where they intersect. All right, so a bit of a heads up, you may have to do something like that on your sack.
May.
Take that as you will, Glenn. All right, exercise 6J.
Do you have an extra sheet for the exercise?
Yeah, I'll print one for you.